Yes, we're starting recording. All right, so this is a position versus time graph. I'm doing this so that it's going to show up on the recording. It's position versus time graph. Each of these increments are by 2, okay? So this is 2, 4, 6, 8, 10. This position is 0, 0. I'm going to stick with 10 for ease, even though the 8 might be directly on the line. I'm going to approximate this as 3.5 on this axis. So I've got 3.5 on the y-axis, 10 on the x-axis. So that's the number I'm going to use. So I've got 0.1 is a 0, 0. 0.2 is 3.5 and 10. All right. So now I'm going to go to the document camera. That's fun. I've got document camera. That document camera. There we go. Too far in. Okay. Maybe. All right. You guys see the two positions? Okay. You guys see the two positions that I've got 0.1 and 3.5 and 10? Thumbs up if you guys see it over Enid. All right, good. Okay, so I was mean, cruel, and wicked. My children will tell you that. My children will tell you I was mean, cruel, and wicked. My previous students will tell you I'm mean, cruel, and wicked, but I'm a fair mean, cruel, and wicked. So if I tell you something is a position versus time graph, so I've said position versus time. Our vernacular says that this is y versus x. So this axis is going to be position. This axis is going to be time. Okay? So I had a point that was 0, 0, and I had a point up here that was 3.5 and 10. If I want to do an average velocity, I'm going to use my average velocity bar. My velocity is my change in position with respect to time. The fact that I had a straight line told me a couple of things. It tells me that I'm at a constant velocity. That's the first thing that I learned. It's a constant velocity. So I want to do my change in position over my change in time. So my average velocity is going to be my position final minus my position initial divided by my time final minus my time initial. Okay, my time final was 10 seconds. My time initial was 0 seconds. My position final was 3.5. We just don't know what units it were. Okay, it could be kilometers, could be miles, could be whatever, but my time was in seconds. And then I've got a 0 there. So I get 3.5 divided by 10, and I end up with, and we said it was meters on the other graph, so I get 0.35 meters per second. Okay. A couple of you gave me the 2.85 as the answer. Well, the 2.85 comes from this right here. If I put 10 seconds on top divided by 3.5, I get 2.85, and I've ended up with the reverse because this is actually seconds over meters. And that's not a velocity. So that's why that one was incorrect. The other two were just numbers I picked out of the air. So I'm not sure how you got 6, because I just literally picked it right out of the air. Okay. So I've gotten several emails over the last 5 days. See if I can do this without getting things screwed up. All right, you should see me over in Tonka, or over in Enid. You see me? Got it. Okay. So over the last 5 days, I've gotten a lot of emails. The emails have been a couple of different kind of terms. Some of them have been question specific, and I'm actually going to go over the questions that I got most of the emails over, or I've had most of the questions in my office over, so I'm actually going to go over them. But I've had a couple or several of you say, the homework doesn't look anything like what we've done in class. All right? The homework doesn't look like anything we've done in class. It is exactly what we've been doing in class. And I'll tell you why you guys think that way. Okay? Because classes look mostly like an algebra class. How many people have looked like we've done algebra or trigonometry for the last 2 weeks? I've got lots of hands. How about you guys over in Enid? Does it look like we've just done algebra and trigonometry the last 2 weeks? Yeah? Okay. Guess what? The language of physics is math. All of our math, up until probably about 1900, came out of physics experiments. That's why we teach physics last. Okay? We have actually done students a disservice because we teach you guys math through elementary school, through grade school, and then we get into high school, and most of you have taken high school biology, right? Everybody took high school biology. You might have taken earth science or physical science, but most of you started out with biology. Why do we start out with biology? How much math is in biology? Especially early general biology, there's very, very little math. So we start with biology because that gives you observation skills, it gives you classifying skills, it gives you a bunch of those skills. And what we're doing over in math class is we're starting with just general math, maybe we're starting with something else over in math class. Then the next logical place is chemistry, right? The next logical place is what we do chemistry. And basically in chemistry, we end up doing mostly conversions. That's pretty much, we do conversions and balancing, so we're using a little bit of math. We're not using as much math as when you finally get to physics, all of a sudden you're using math. But over in algebra class, you guys have been doing word problems. Fred started out traveling at 10 miles an hour, and he goes for 3 hours. Joe starts out 3 seconds later and is traveling 5 miles an hour and travels for 15 minutes. Who's further down the road, Fred or Joe? That's an algebra problem. Guess what? That's a one-dimensional motion physics problem. That's exactly what we've done. What we have done to you is we have broken math and physics. We have not kept it together. We have broken it apart, so you guys have been looking at algebra all this time, and you're going to tell me, well, if I just knew what equation to use, I could do the problem. Unfortunately, right now I can do that, okay? Right now I can give you the tools and tell you which equation to use, but when we get to momentum, when we get to forces, when we get to other things, you're going to have to create your own equations. It's what you're going to have to do. So the first thing is, you know how to do all of this. You know how to do all of this, except you checked your brain at the door because you came in and you said physics is tough. Physics is hard. Physics is going to be the worst class I've ever taken. No. Physics isn't all that hard. Physics isn't all that tough. We just talk a different language. We actually speak the language of math. That's how we actually talk. In fact, I learned how I ended, so you guys know I'm weird. I'm also a physicist, so that just, gives me permission to be weird, right? Gives me totally permission to be weird. If I came in here and my clothes didn't match, you guys would go, oh, she's just a physicist. It's okay, right? That's exactly what you guys would do. But what happens is we're going to talk it sounds like we're talking a different language. So the first thing is you guys learned the language. So it's like going to Spanish class and learning the vocabulary, but then all of a sudden you're in Mexico City and you have to actually speak Spanish. It don't work, right? It doesn't work. If you throw me into France and actually make me have to speak French, I can maybe read the signs, right? But I certainly can't have a really good conversation. A 3-year-old's probably gonna have a better conversation than I am. It's because what we've done is we've broken it apart. So everything that we have done up to here, you guys are gonna use. But the first thing we got to do is we got to patch it back together. We've got to patch the meaning back together from what you guys had had. And so why it doesn't look that way is that you've never had to think about that before that way, okay? It's always been the part of algebra that most of you said, how many of you liked word problems in algebra? Okay, somebody loves word problems. Come on. Physics is a bunch of word problems. Okay, that's essentially what we've got. Physics is a bunch of word problems. So that's what's happened, is we've broken it apart. The other part of it is, anytime that you think about something or you panic when you first actually go in to read the problem, that's going to be one of the things that really causes you an issue. The other part is, we've also done, while online homework is a positive thing, it's also a negative thing. How many of you did your homework with a piece of paper right beside you? I want honest answers. I got about, over here I got about 2/3. I got about 2/3 over there. There's a third of you that did not take out a piece of paper. That means if you didn't take out a piece of paper, you didn't draw a picture. If you don't draw a picture, it's really tough to figure out what the problem is trying to tell me. That's the first thing. So drawing that picture really, really hugely makes a difference. The other part of it is, if you read the question and you panic, you go, oh my gosh, I've read the question, I've panicked, now I don't know what to do. Stop. Read the question out loud. I know it sounds hokey, but read the question out loud. It makes a huge difference. Writing, and for some of you, write out the whole question, because then you can underline certain things that make it help it make sense. So that's those are things that are going to actually help you get through this. Not doing it is only going to perpetuate the problem. There is no way that I cannot give you, at the end of the semester, a comprehensive exam. Try as I might, it's not going to happen, because everything that we're going to do builds on itself. So that's one of the things. So if you've got to get these parts kind of grounded, because we're just going to build on itself and build on itself and build on itself. So that's one of the issues that you've got to kind of look at. Study buddies. I explain it one way. I've got the videos out there. I try to upload them so that you guys get the closed captions so you can actually read what I'm saying. Google or YouTube is not the best, but it's pretty darn good. And so you want to actually read the subtitles, because that may help you. Because some of you, hearing it works. Some of you, reading it works. Some of you, talking to another student is going to make it work. On the Enid campus, Dr. Monroe, Dr. Samamano, and even Mr. Orzel, who does the earth science, they're all willing to help you and tutor for you. Over here on the Tonkawa campus, we will have tutors that we just haven't posted the announcement of exactly when tutors are. But the two math tutors, Kristen Phelps and Riley Smith, both can help you with physics problems, okay? All right? Because basically all we've done so far is math word problems. That's basically all we've done so far. The other thing that you guys will find out is you will second guess yourself. You're going, oh, it can't be that easy. A lot of times it's that easy. Physics is elegant. The solutions to physics are actually elegant. So a lot of times it really, truly is that easy. I will warn you when we get to an ugly problem, because the algebra gets ugly. It's not that the problem's hard, the algebra just gets ugly. And I'll warn you when we get there. But for right now, the simpler solutions are actually probably most correct. The other thing is, use your units, because your units are really, 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 really going to help you make sure that you've got things straight. Just like the example that I did just now, where if I had it reversed, the position, I did it a little tricky because I didn't actually give you what was on that y-axis and what was on the x-axis. I told you position versus time, but that's where we're going to be at it. So don't panic. And go ahead and email me. I think most of you figured out, those of you who emailed me, unless it was Saturday or Sunday, I didn't get to write back, but most of the time I get back within a couple hours, unless it's after 5 o'clock, okay? So definitely. And for those of you guys over in Enid, I've got a couple of ways that I can work with you over the phone. I've got a couple of ways that I can show you a whiteboard and actually help you with a problem on a whiteboard, as long as you have internet access, okay, at the time. So, but again, you can answer questions and go from there, okay? Everybody good? So that's my pep talk. We got a pep talk. So now let's work some of the problems. And I will warn you, there are a lot of palm to forehead moments. Okay? Palm to forehead moments. And if you want to kind of understand that that's part of learning. Okay? That is part of learning. Learning is not easy. And for most of you, the two classes where you first start to struggle, because what we do in the school systems now are chemistry and physics. Those are the first two classes where you just can't walk in and get all your homework done before you leave school. It's just the way we are. All right, so let's go to the document cam and let's work the two problems that maybe. There we go. So I'm going to start with this problem. This looks very, very much like one of the problems that you guys had. Your problem had a graph that it is a position versus time graph. This is what we have, is a position versus time graph. I just didn't go below the y-axis or below the x-axis on here. So this is position. And I'm going to go ahead and give it units. So that's actually in meters. And this is time. So that's actually going to be in seconds. Couple things that we know. If I were in algebra class, they just give you the graph, right? I've now told you it's position versus time. We just gave you the graph, okay? In physics, we can say, oh, let's do Jose is walking, and this describes his motion. So in the first 2 seconds, Jose goes from 0 meters to 2 meters. And then Jose is going to sit there and he's going to stand there waiting for the crosswalk light to go. And he's going to sit there for a second, and he sees something behind him, and he's got to go pick up the quarter on the sidewalk. So he's going to actually go backwards a little bit, picks up the quarter, and then realizes he missed the crosswalk, right? We missed the crosswalk, so now I'm going to sit right there. And I'm waiting because I'm not that far from the edge of the street. And now I'm going to cross the street, and I'm going to be up there. So in those 5 seconds, we walked up to the crosswalk, we stood at the crosswalk, wait for the light, go back, pick something up, wait for the light again, and now we've actually crossed the street. So what I've told you in this graph, so in algebra class, we just gave you a graph. In physics class, we've told you that this corresponds to motion. What did you guys do in your very first lab? You did exactly this, right? Yes. Except you tried to match a graph, which was like loads of fun, right? Trying to match that graph, partially because if you had, depending on whose shirt you were using, that always interfered with stuff. But basically, this is exactly what you did in the first lab. We're trying to put the math and the physics back together. All right, so good old Jose is out there. So now I can ask you some questions. So types of questions I can ask you is, at what position is Jose at 3.2 seconds? Okay, what position is Jose at 3.2 seconds? Well, I go to my graph, and I'm going, all right, this is 3.5, okay? And this is like okay, that's at 3.2, so I can go up here. And that's where Jose is standing at 3.2 seconds. And that looks like it's, let's see, this is 0.2, this is 0.4, this is 0.6, this is 0.8. That looks like I'm at 1.8 meters. So I can read position right off of this graph at any time between 0 and 5 seconds. Okay, so the problem that you guys had said something like this. We had a tennis player move. Everybody remember the tennis player? We had a tennis player move in a particular pattern. We had a graph in that tennis player. And we wanted to find the average velocity. We wanted to find the average velocity between various times. So we want to find the average velocity between, let's do 1 second and 4 seconds. Very similar to what your homework problem was. Well, first thing I got to remember is my average velocity is my change in position with respect to a change in time. Okay, my average velocity is change in position with respect to time. I'm going to turn off this light because it looks, on this screen, it looks a little funky. See if this makes it look a little better. It's a little better. That's why usually why I write with a bigger marker, but I want to be able to do several things on the same page here. So first thing I have to know is what change in position means. Change in position means my position final minus my position initial. Okay? And same for the time. This is my time final minus my time initial. So the first thing I got to do is at 4 seconds, so I'm over here at 4 seconds, the position is 1. At 1 second, my position is 1. So if I go in here and I put my final position is 1 meter minus my initial position, which is 1 meter, and my final time was 4 seconds minus my initial time, which was 1 second, I get 0 divided by 3. Guess what? I'm at 0 meters per second. So the average velocity is 0. Okay, my average velocity is 0. But I can do the average velocity for this one between 5 seconds and 0 seconds. So it's overall average velocity, change in position with respect to time. My final position is 3 meters. My initial position was 0 meters. My time was 5 seconds. My initial time was 1 second. I get 3/5. I'm in meters per second. And when I plug that into the calculator.
Could you put your paper up, please?
Hang on. Let's see if I can get this. Did I get it?
Yes.
Okay. So that's 0.6 meters per second. And basically all I did was take my different positions. There was the 0 position, so that was at 0. Here's my other one. This is at 3. My change in position with respect to time. My units, because we know that velocity has to be in meters per second, my units clearly help me out to know that I've set it up right. And so all of good old problem, this problem right here, my tennis player, was just that. Was just reading positions off of the graph, doing the calculation between my change in position with respect to my change in time. Now, just in case, back here, I'm going to go to the computer. thinking about it. All right. Okay, so you should see my version of WebAssign. I'm going to go to what you guys see in WebAssign. And most of you see my classes, my books, right? So most of you have got that class right there. So here is the page that you get right when it comes up. All right? This is the next homework assignment. It's homework chapter 3. It's going to be due next week. We'll get there. And if I want to go back and look at my past assignments, okay, I want to go back and look at my past assignments. Here's my past assignments. And everything that we've already done is right there. So you have the way to go back to all of your past assignments. So if you want to go back to homework 2, there's my homework 2, and now you can go back and look at it. And now you can also view the key. So once the homework is due, you can go back and see the homework problem. So if you've missed one, you can view the key. So if I view the key, it will tell me, it'll show up, and it will also show me the solution. So you guys have the solution to the problem. So our good old tennis player here, there's my tennis player. There is the whole set of calculations for my tennis player. So you can go in there, the change of position with respect to time, and you can actually see the whole thing. It's also important to look at the order, okay? Because this one we were looking at, I was over here, and I was in the negative spot. I have to make sure I get my negatives in the right spot, otherwise it's not going to give me my right values. So you have to keep track of direction. So in one motion, we go positive and negative. In 2 directions, we're going to still go positive and negative in those different directions. So that's how you can get back to your actual homework. Also, you usually have these buttons that have the read its, and the read its will take you right to the section of the book where that stuff is discussed. So it takes you right back to that section of the book. So the read its are actually really helpful. So if you're not understanding the problem, you can go to the read its. And when we get here, so you can also look at, so we're in motion in one direction. I'm going to do my free-falling objects here. Okay, my free-falling objects. You've got examples in here, and I can actually page through. You've got this example here, not a bad throw for a rookie. This example, I'm going to warn you right now, we're going to see it over and over and over again. And on a test, if I've seen it as an example, I've seen it done as something else, you're going to see it over and over and over again. Guess what the likelihood of that you're going to see that one on a test? Pretty high. Okay, pretty high. So this example will be a really good example to look at. And it also goes through, and I like this example because it goes through and it tells us a lot of different information. So that is example 2.5. We'll actually kind of, if I've got time today, we'll actually kind of dive into it. But I'm actually going to take a step back and go over a couple of other pieces to make sure you guys got it solid because we're building on those things. So that helps you out in WebAssign. The other thing that you have back in WebAssign, if I go back here to student view, and these are all open for you. My glasses. These are personal study plans. So if I open this, it has practice quizzes and tutorials, which is one of the reasons why I like online homework. Online homework gives you instant feedback, and it gives you things like these practice quizzes and tutorials. So you do have an opportunity to actually get those pieces in there. And I want to double check something while I'm over here. Because trying to keep track of my classes this semester has been entertainment deluxe. If I go into my courses, come down here, general physics. Yep, there is a quiz. I thought there was. And course materials and assignments. Let's go to week 2. There's the quiz. Okay. And let me look at the test options real quick. Last grade attempt, so play after the 31st, and it was due by noon. So just making sure the quiz was in there. All right. And some of you want to know why I'm a stickler for homework being and not provide extensions. I used to work as an environmental consultant. I used to work as an environmental compliance person for oil companies. And EPA does not provide extensions, even when it's EPA's fault. So if you are trying to input your report that is due by midnight and EPA's file goes down, EPA says, it's your fault, you didn't do it on time. Even though EPA's system went down, it's your fault, you didn't do it on time. And you can get $25,000 per day per line on that report is a potential fine. So there's a reason why I'm a stickler for deadlines, because it doesn't matter, the real world doesn't give you extensions. Sometimes the real world gives you extensions. Most of the time, the real world doesn't give you extensions. Now, that being said, if you know in advance that you're going to have a problem, holler. Or if it's a true emergency, holler. Oh, what did I have the quiz due at? 8 a.m. Yeah. And remember, I do drop quizzes. Okay, there are a couple quizzes that I will drop. So, all right. So now let's look at a different problem here. Different problem. All right, we have a motorist. This was another problem that people had. We had a motorist that's going to drive north. Let me use a different marker. Okay, it's told that our motorist was going to drive north, so I'm going to drive north on my piece of paper, maybe, so where we can see it. And we're told that the motorist is driving north for 30 minutes at 89.5 kilometers per hour. Then we're going to sit at a spot for 15 minutes. Then we're going to continue driving north, and we're traveling at 130 kilometers per hour, and we're traveling for 1.6 hours. So this is our motion. It asks us, what's the total displacement? And the average velocity. All right. So basically, I've got some things that I got problems with. First problem is I've got mixed units. I've got minutes and I have hours. So I'm going to go ahead and convert this to hours. And we all know that 15 minutes is 0.25 hours. And 30 minutes is 0.5 hours. So now I can calculate total time. The total time is 1.6 plus 0.25 plus 0.5, and this is going to be in hours. And your numbers may have been slightly different. So this tells me I traveled 2.35 hours. Well, now I need to know distance because it wants total displacement. So I need to know what my x is. All right. and I've got, and I'm going to write out the physics equation. Velocity is equal position divided by time, or my position is going to equal velocity times time, or I can write it in terms of distance is equal to velocity times time. And guess what? We've been doing those problems. We do those problems in our head. If I have to travel to Oklahoma City from here, I'm in Tonkawa today, so if I have to travel from Oklahoma City to here, it's roughly 90 miles, right? If I'm traveling at 60 miles an hour, how long is it going to take me to get to Oklahoma City? Come on. An hour and a half. Okay? That's no different than what I've just done here. Except this time I'm saying I'm going to travel an hour and a half at 60 miles an hour. How far did I go? 90 miles. No different. But I'll bet you all went, I have no idea how to do this problem. Because it's in physics class. So it's scary. You've been doing this problem since you learned how to drive. That's the only difference is instead of driving in miles per hour, they drove kilometers per hour. Okay? So I'm going to take my 89.5 kilometers per hour, and I'm going to multiply it by 0.5 hours. My hours are going to cancel. 89.5 times 0.5 tells me that it's 44.75 kilometers. Do the same thing at the top, 130 times 1.6. So it's 130 kilometers per hour times 1.6 hours gives me 208 kilometers. So now I can do total distance. That's my 2.08 kilometers plus my 44.75 kilometers is equal to 252.75 kilometers. So my total distance is 2.7 or 2.52 kilometers. Now I can look at what I wanted to know. I wanted to know total displacement. Where I started and where I finished. My total displacement, 2.5275 kilometers. My average velocity is my change in position with respect to my change in time. So I'm going to do my 25275 kilometers and my total time, which was 2.35 hours. 2.35 gives me 107 kilometers per hour. Or 108 kilometers per hour because it's 1.755 when you plug it into the calculator. I just don't have room on my piece of paper. Okay. So the next problem, let's do the other one, because the other problem I have that people had trouble with was very, very similar to that one. The next one was this one. And I probably had more questions about this one than any of the other ones. Okay, remember on Friday of last week, I said there was a problem that you had to go into. They gave you a formula, and you were going to have to calculate, using that formula, the position. Then you were going to have to use the position in order to calculate the interval, and you were going to have to carry the extra significant figures. This was the problem. Okay? This was the problem. So, the formula they give us, so this formula, the one I have on my piece of paper, everybody probably had a different one, was 4 meters per second times time plus 0.85 meters per second cubed times time cubed. It wants me to find at a change in t of 0.4 seconds, and it gave me t1 was equal to 3.4 seconds, and t2 was equal to 3 seconds. And I wanted to find the instantaneous velocity for that time interval. So my velocity is my change in position with respect to time. So what I needed to do is I need to find position 1. Position 1 is going to be 4 times 3.4 seconds plus 0.85, and I've got 3.4 seconds cubed. So I plug that into the calculator. And do it this way. 3.4 times 3.4 times 3.4. That gives me 39 times 0.85. Gives me, this part becomes 33.4. Gives me 13.6. Gives me 47 meters. I do the same calculation for the other time. So x2 is 4, and it's going to be at 3. And I've got my 0.085, and I've got 3 cubed. So I have 9 times 0.85, 7.65, and this is 12. Gives me 19.65 meters. So now I'm doing my change in position. With respect to time. And in this case, we want this one versus that one. So even though I've written 1 and 2 down, it's a little, I've got it reversed. So I'm going to have my 47 minus my 19.65 meters divided by my 0.4 seconds, because that's the difference in my time. Gives me 68.375 meters per second. Then they wanted you to do it again, except instead of 0.34 and 0.3, it wanted you to do it 0.30 and 3.1. So our delta time now was 0.2. And then it wanted you to do it a third time and have you get the delta, my delta time was equal to 0.1. And you would see that those numbers on that end changed as I was approaching that smaller and smaller and smaller time interval. This one was just about crunching the numbers. Question from over there?
Yes, on X2, are we cubing 3 or are we just squaring it?
You're cubing it because the equation it gave you was this. Meters per second cubed and time cubed.
Yes,
Your answer is squared.
2 squared is 27 and not 9.
Oh, okay, sorry. So that goes there. I didn't actually punch it in the calculator. So that becomes 39. So then if that becomes 39, then I get 47 minus 39. That becomes 8. And that became 8 divided by 0.4. Became 20 meters, 20,000 meters per second. And I'll bet that was several times since the people who got it right ended up doing the exact same thing I just did and put it in the website and went, wait a second, I thought I did it right. Okay, so hopefully that makes the homework a little clearer. So let's look at our guy on top of the building. Example 2.5. Well, first of all, let's look at where we ended up on Friday. On Friday, I got a toolkit, and my toolkit was my position, my change in position, or my change in x, was equal to my velocity. Now, that could be an I or an O, but that's my initial velocity, plus 1/2 AT squared. So this is in terms of x, a, and time. I have velocity squared is equal to my initial velocity squared plus 2 acceleration change in time. So this is in terms of velocity, acceleration, and position. And then I had velocity, velocity was equal to my initial velocity plus my acceleration times time. And this was in velocity, acceleration, and time. So those are my 3 equations. I also have this one hanging out there. Where I have no acceleration. But that's a special case of this one, okay? That's a special case of this one. So those are my 3 kinematics equation of motion. So what we're going to do is we're going to look at, I'm standing on a cliff. There's water down here. We're going to toss the ball up, okay? There, now you guys can see the water. I'm going to toss the ball up, and I don't necessarily know, but I'm tossing the ball up with an initial velocity. It's going to go up, it's going to reach the top, and it's going to fall back down, and it's going to just miss my building here, or my cliff and my water, and have a splash. All right. So we're going to toss the ball. And when it gets to this point, I'm going to start a timer. And we're going to time the time that it takes to hit the splash. And we're going to make the assumption that there's not a big difference in time between hitting the splash and when I start the clock, so that this is going to actually be the time of fall. So we're going to have that time of fall, and my time of fall is going to be 0.36 seconds. Now, I'm telling you right now, I'm just pulling these numbers out of my head. Okay? Pulling these numbers out of my head. I'm going to actually, I haven't done this ahead of time, so it's not one that I've actually not done nice and pretty. Okay. Now, I can find lots of information based on what I have. There's something I know that I haven't given you in the problem at all, but some of the things we want to find. We want to find the height of the cliff. Okay? We want to find the height of the cliff. I want to find, let's see, I think I do need to give you one more piece of information. So we're going to actually know my initial velocity. I'm going to actually give you our initial velocity. So we're going to give an initial velocity of 2 meters per second. So we're going to start with an initial velocity of 2 meters per second. It's given in the problem. I want to know the height of the cliff. I want to know this height. I want to know the total time of fall, or the total time that's out of my hands. And I want to know the velocity when it hits the ground, or velocity when it hits the water. Okay? I want to know all that information. There are two things on my picture that I know that they haven't told me in the problem. I know the velocity at the top. What's the velocity at the top? 0. Because what's happening at the top is I'm going up, and then at the very top I'm going right down, and so it's got to go through 0. So the velocity at the top is 0 meters per second. I know something else.
Acceleration.
Yep, I know my acceleration. My acceleration is my acceleration due to gravity, and it's a negative 9.8 meters per second squared. And we're going to use the 9.8 meters per second squared. Let's see. Did you guys calculate gravity in the lab last week? You did motion on an inclined plane last week, right? If I did motion on an inclined plane, I actually could get gravity. Did you actually calculate it? Yeah, you can get motion, you can get gravity. We'll end up measuring gravity a lot, but we can get gravity. So I've got gravity. So I have a variety of things. So let's start plugging in some problems. One of the things is you don't always have to do the problem in the order that WebAssign gives them to you. Okay? Sometimes it may be easier to do certain parts of the problem first. So for example, all right, I'm going to calculate, I want the total time out of my hand, so I'm going to need time several places. I want the total height here. I'm going to break this problem up into two parts. I'm going to break this problem up right here. I'm going to look at this half of the problem. So I'm looking at this half of the problem. So if I look at that half of the problem, I know my initial velocity, I know my final velocity. I have an equation that helps me. So there's my final velocity squared is equal to my initial velocity squared plus 2a change in x, which is going to be my initial velocity squared plus 2a times the height above my block. I know this, I know that, I know that. That is 0. So now I get the velocity minus 2 gravity height is equal to 0. That's velocity squared, sorry. Velocity squared 2 height is equal to 0. So now I can solve for height. So I'll keep my picture handy. The velocity squared is equal to 2gh. Velocity squared is equal to 2g is equal to h. This we said was 2 meters per second squared. 2 times 9.8 meters per second squared. This is going to help us out. So I got meters squared, second squared, divided by meters, divided by second squared. Second squares cancel. One of those meters cancel. I end up with meters. Woohoo! I've set my problem up right. I'm going to get a height. I get 4 divided by 2 times 9.8. You'd think I'd remember that number. 19.6. So now I've got 4 divided by 19.6 is equal to 0.2 meters. And this is the height that goes from here to here. This is this part. The second part is going to be this height. Okay? So this height from here to here is 0.2 meters. Well, I need to know this time, because we know this time, right? We know this time. This was given in the problem. So I need to know this time that I've got out there. Well, I can go back to this problem right here. My velocity is equal to my initial velocity plus my acceleration times time, so I can do that part. So velocity is equal to velocity initial minus gravity times time. This velocity at the top was 0. So velocity initial divided by gravity is going to equal the time to top. So this is 2 meters per second divided by 9.8 meters per second squared. Meters cancels, one of the seconds cancels. I end up in seconds, so I know I've set it up right. I get 0.2 seconds. So that's the time that it took to go to the top. Now, I can do a couple of things. One of the things is I can actually calculate the other side. Or I can look at my problem and look at exactly what's happening, and I know that the time that it takes to go up here is the same time that it takes to come back down there. I can do it by symmetry. So the time that it takes to go up and the time that it takes to go down is the same time. So now I have 0.2 seconds. So time total is equal to 0.2 plus 0.2 plus 0.36. It's going to equal 0.76 seconds. That's the total time that the ball is out of my hands before it hits the water. That was one of the things we wanted to find out. All right, so I know the height's to there, but now I've got a problem down here. I need to know this height. Okay, well that height is going to be this part here. I've got an equation that helps me. I've got 8x is equal to my v initial times time plus 1/2 at squared. I know by symmetry when it passes this point, it has an initial velocity, except now it's a negative 2 meters per second because of symmetry. I start up with 2 meters per second. I got to come down at negative 2 meters per second. My initial velocity was 2 meters per second. Initial velocity, 2 meters per second. So now I have acceleration, because that's gravity. I have this, and I've got time, so I can calculate h. H is going to be negative 2 meters per second. My time is 0.36 seconds. Seconds cancel, so I know I'm in meters. That's good. I have to have negative because gravity's going down. I got 1/2 9.8 meters per second squared. My time is 0.36 seconds, and that's going to be squared. So now I plug it into the calculator. This becomes a negative 0.72. And this becomes a negative 0.65 or 0.35, 0.635. So this is going to equal a negative 1.355 meters. So this distance here, 1.355 meters. It's negative because I'm going down, and it's below my initial position. But the question is going to ask me, what's this total height? Well, that total height is that combined, it's my 1.355 plus my 0.2 gives me 1.555 meters for the total height that I fell. So depending upon which question is asked, depends upon which number I'm going to actually use and calculate. Okay, looking at the equations that I used, in this one, I knew my initial velocity, I knew my acceleration, and I knew my time, so I could find position. This one gave me position and my velocities. I didn't have to know time in order to calculate the height. And then I can do, now, we want to do our last one. We want to know our velocity when it hits the water, right? We want to know our velocity when it hits the water, so let's do the last one. I knew there was one more I wanted to do, because I wanted to use all the equations. So let's look at our picture now, what we know. We know that this height is 0.2 meters. We know that this is 1.355 meters. So we have a total height of 1.555. This is all in meters. We have, this is 0.36 seconds. This is 0.2 seconds. And this was 0.2 seconds. We have an initial velocity of 2 meters per second. We know the velocity up here at the top is equal to 0. And I have an acceleration due to gravity of minus 9.8 meters per second squared. So we have lots of information now. And now we want to find the velocity at that point. So I have velocity is equal to initial velocity minus gravity times time. If I do this, this total time is 0.56 seconds. My velocity here is equal to 0. So my velocity final is going to be 0 minus 9.8 meters per second squared times my time of 0.56 seconds. Seconds cancel, so I end up in meters per second. Gives me a negative 5.488 meters per second. The negative tells me I'm going this direction. That's what that negative tells me. So it tells me I'm going down at 5.48 meters per second when it hits the water. So I can find out lots of information about my problem. And my guess is brains are full. Yeah. Well, I don't want to start anything else in the next 10 minutes. Don't want to introduce a new topic in the next 10 minutes.